The serene beauty of the night sky is a lie. The universe is not a peaceful kingdom. It is a violent forge where chaos reigns. Every atom in your body, the iron in your blood, and the calcium in your bones is a survivor of ancient cosmic collisions that would shatter our world in an instant. Prepare yourselves for a voyage into power beyond imagination. Today, we journey into that fire. We begin not in the quiet, empty blackness we often picture, but in a cosmos defined by unimaginable violence. Think of forces so immense they can warp the very fabric of space-time collisions, so energetic they can outshine 1 billion suns, and impacts so transformative they can give birth to worlds and dictate the course of life itself. In the grand narrative of the cosmos, the story of creation is inextricably linked with the story of destruction. They are two sides of the same cosmic coin. This is a universe not of quiet majesty, but of a roaring, chaotic, and unending series of cataclysmic encounters. These events are not aberrations. They are the very architects of existence. Our journey will take us directly into the heart of this violence. You will witness the dramatic spectacles and understand their profound impact on everything we see today. You will see how the moon that graces our night sky was born from a planetary cataclysm, a beautiful scar left by a lost world. You will see how the gold on your finger was forged in the death dance of two stellar corpses, objects so dense they defy comprehension. And you will see how our own Milky Way galaxy is hurtling towards a destiny-altering crash with its giant neighbor Andromeda. This is the story of how everything we see, from the smallest planet to the largest supercluster of galaxies, was shaped in the universe's violent cradle. So how do we make sense of a universe built on such destructive principles? The key lies in redefining our perspective. We must learn to see not just the explosion, but the elements it scatters. We must see not just the shattered galaxies, but the brilliant bursts of new stars born from their wreckage. This is the central lesson of the cosmos. Destruction is the engine of creation. Every end is a new, more complex beginning. The universe is a phoenix constantly burning itself down, only to rise again from the ashes more structured and more beautiful than before. As we embark on this voyage, hold this duality in your mind. We are not just witnesses to destruction, we are watching the very process of cosmic birth. The next time you look up at the silent stars, remember that you are witnessing the aftermath of 1 billion ancient battles, and you yourself are one of its greatest victories. The invitation is open. Let us begin. For most of human history, the universe was a place of serene, predictable majesty. Before the Milky Way had a name, ancient eyes looked up and saw not chaos but order. They saw the celestial spheres, a series of perfect crystalline shells, with the Earth at their center, a divine model championed by thinkers from Aristotle to Ptolemy. The stars wheeled overhead with the precision of a grand celestial clockwork, a comforting and eternal dance. The heavens were considered a realm of perfection, unchanging and incorruptible, a stark contrast to our own transient and chaotic world below. For millennia, this geocentric view was not just a scientific model. It was a philosophical and spiritual anchor, giving humanity a clear and central place in a cosmos designed for us. This was our first and most profound illusion. Then came a crack in that illusion. A Polish astronomer, Nicholas Copernicus, dared to propose a radical idea that the Earth was not the center of everything. Instead, he placed the sun at the heart of the cosmos, demoting our world to just another planet. His theory was elegant, but it lacked definitive proof. That proof would come from the telescope of an Italian mathematician, Galileo Galilei. When Galileo pointed his simple instrument at the heavens, he shattered the crystalline spheres forever. He saw that the moon was not a perfect, smooth orb, but a world covered in mountains and craters just like Earth. He saw that the planet Jupiter had its own moons, a miniature solar system that did not orbit the Earth. These were not just observations, they were acts of intellectual revolution. The old, comforting picture of the universe began to crumble. Yet from the rubble of one illusion, another more sophisticated one arose. Men like Johannes Kepler discovered the precise mathematical laws governing planetary orbits, and Sir Isaac Newton unified the heavens and earth with his universal law of gravitation. The universe was no longer a realm of divine mystery, but a magnificent machine, a clockwork universe, governed by knowable, predictable laws. Gravity was the master clockmaker. If you knew the position and velocity of every particle, you could, in principle, predict the entire future of the cosmos. This new vision was empowering. The universe might be vast and indifferent, but it was orderly, it was safe. But what if this grand clockwork was an illusion of a different kind? What if the very laws that promised order contained the seeds of unimaginable chaos? The final shattering came in the 20th century. Using the giant telescopes of his day, an American astronomer named Edwin Hubble made two discoveries that would tear down the clockwork universe forever. First, he proved that the faint spiral-shaped nebulae were not clouds of gas within our own Milky Way. They were entire separate galaxies, island universes, containing billions of their own stars, located millions of light-years away. The scale of the universe expanded in an instant from a single city of stars to a cosmos of countless cities. Then came the knockout blow. Hubble analyzed the light from these distant galaxies and found that almost all of them were shifted towards the red end of the spectrum. This red shift was the cosmic equivalent of a siren's wail receding into the distance. It meant the galaxies were not static. They were all flying away from us and from each other. The universe was not a static machine. It was expanding. The old picture of a still eternal universe was gone, replaced by a reality of relentless dynamism, a place of hidden motion where galaxies are on billion-year collision courses. We've stepped out of the quiet safety of the clockwork and into a story of gravitational chaos, a story where collisions are not accidents, but an inevitable consequence of the universe's own evolution. The illusion was shattered, and for the first time, we could see the cosmos for what it truly is, a violent, beautiful, and creative forge. What is the engine driving this cosmic chaos? What is the force that choreographs this ballet of destruction and creation? It is the most familiar, yet most profoundly misunderstood force in the universe: gravity. For centuries, we understood gravity through the eyes of Isaac Newton as a mysterious, invisible force, a spooky action at a distance that one object exerts on another. It was a pull, a tether, that reached across the void to keep the planets in their orbits and the stars in their galaxies. But this picture, while revolutionary for its time, was incomplete. It could describe the how of gravity, but not the why. Why does this force exist? How does it travel across empty space? The answer would require a complete reimagining of reality itself, a vision from the mind of Albert Einstein. To truly understand gravity, we must abandon our everyday intuition. Picture space not as an empty stage, but as a vast, flexible fabric. Now picture time not as a separate ticking clock, but as another dimension inextricably woven together with space. Einstein called this unified four-dimensional reality space-time. This is the true arena of the cosmos. Now let's use a classic thought experiment. Imagine placing a heavy bowling ball onto a stretched rubber sheet. The ball sinks into the sheet, creating a deep well, a curvature in the fabric around it. This is what mass does to space-time. A planet, a star, a galaxy, each one warps the very geometry of the universe around it. Gravity, Einstein revealed, is not a force that propagates through space. Gravity is the curvature of space-time itself. With this new understanding, the motion of the heavens is no longer a mystery. A planet orbiting the sun is not being pulled by an invisible rope. It is simply following the straightest possible path through the curved space-time created by the sun's immense mass. It is like a marble rolled near the bowling ball on the rubber sheet. It appears to be pulled towards the center, but it is merely following the contours of the sheet. This is gravity's grand design. It is elegant, profound, and far more powerful than Newton ever dreamed. It means that the universe is not just a collection of objects in a passive, empty void. The objects and the space they inhabit are in a constant dynamic interplay. Matter tells spacetime how to curve, and the curvature of spacetime tells matter how to move. And what does this mean for cosmic collisions? It means they are inevitable. A collision is not merely two objects accidentally bumping into each other in the dark. It is the dramatic, predictable climax of two or more objects following the invisible contours of spacetime, spiraling down into a shared gravitational well of their own making. Think of two galaxies approaching each other. It is their immense masses magnified by their vast halos of dark matter that create a deep shared depression in the fabric of spacetime. As they draw closer, they are not just pulling on each other. They are sliding down the walls of this cosmic valley, their paths converging towards a single cataclysmic destiny at the bottom. Gravity is the architect, the sculptor, and the ultimate destroyer. It is the engine of change, the relentless force that ensures the universe can never be static forever, driving matter together to fuel the fires of its own transformation, destruction, annihilation, cataclysm. These words carry a sense of ultimate finality, of an irrevocable end. In our human experience, they represent loss and tragedy, but in the grand lexicon of the cosmos, they are inseparable from a different word creation. This is perhaps the most profound and counterintuitive lesson the universe has to teach us. In the cosmic arena, every end is a new and often more spectacular beginning. The universe is a phoenix, a mythical bird that is consumed by fire, only to rise again from its own ashes more beautiful and powerful than before. To understand cosmic collisions, we must embrace this duality. We are not just witnesses to destruction. We are watching the very process of cosmic rebirth. Consider the death of a massive star. When a star many times more massive than our sun exhausts its nuclear fuel, its core collapses under its own immense gravity, triggering a cataclysmic explosion known as a supernova. For a brief moment, this single dying star can outshine its entire host galaxy, unleashing more energy than our sun will produce in its entire 10 billion-year lifetime. It is an event of unimaginable violence, an act of stellar self-immolation that tears the star apart. But in its death, something miraculous happens. The extreme temperatures and pressures inside the explosion forge the heavy elements of the periodic table, the carbon in our cells, the oxygen we breathe, the silicon in the rocks beneath our feet, and the iron in our blood. These newly minted elements, the very building blocks of planets and life, are then blasted out into the interstellar medium at incredible speeds. The death of one star seeds the cosmos with the raw materials for the next generation of stars and for worlds like our own. The explosion is not an end. It is a creative act of cosmic dispersal. Now let us zoom out to an even grander scale. Imagine two vast spiral galaxies, each a spinning city of 100 billion stars on a collision course. As they merge over hundreds of millions of years, their elegant structures are torn apart. Stars are flung out into the void in long, ghostly tidal tails. The orderly dance of stellar orbits descends into gravitational chaos. It is a scene of cosmic demolition on a scale that dwarfs any stellar explosion. But look closer into the heart of the collision. As the vast clouds of interstellar gas and dust from each galaxy slam into one another, they are compressed, triggering a firestorm of new star formation. A starburst ignites, creating millions of brilliant hot young stars in a relatively short period. The merging galaxies light up with a brilliance they never knew in their quiet, isolated lives. From the wreckage of two old galaxies, a new, more massive and more vibrant stellar metropolis is born. The collision is a process of cosmic recycling on the grandest scale imaginable. So as we journey into the heart of these cataclysmic events, we must hold this duality in our minds. We must see the beauty in the violence, the order in the chaos, and the creation in the destruction. The universe is not a gentle garden. It is a violent, churning forge. And it is this very violence that makes complexity and ultimately life possible. The phoenix is not just a myth. It is a fundamental principle of the cosmos, written in the language of exploding stars and colliding galaxies. Our exploration of cosmic collisions will be a journey through scale, a voyage that begins with events that shaped our own world and expands outward to encompass the fate of entire galaxies. To truly grasp the scope of these cosmic encounters, we must travel from the familiar to the unimaginable, from our planetary doorstep to the very edge of the observable universe. This is a fundamental technique in cosmology to understand the whole. We must start with the parts we know best, and then progressively zoom out, letting the universe reveal its structure layer by layer. Our journey begins here at home. We will start in the chaotic youth of our own solar system, a time when our cosmic neighborhood was a crowded and violent demolition derby. We will witness the brutal, world-shattering impact that is thought to have created our moon, an event that transformed the Earth forever and set the stage for the emergence of life. We will then fast forward through geologic time to stand witness to the cataclysm that ended the reign of the dinosaurs, a stark and chilling reminder of life's inherent fragility in a cosmic shooting gallery. These are collisions on a scale we can almost comprehend, events that directly shaped the history of our planet. Leaving our solar system behind, our journey then takes us into the vaster, more dynamic arena of the galaxy itself. Here in the realm of the stars, we encounter collisions of a different kind. We will see how close encounters between suns can wreak havoc on planetary systems, ejecting worlds into the cold, lonely darkness of interstellar space. We will then venture into the realm of the dead to witness the spectacular collisions of stellar corpses. We will watch as white dwarfs, the dense embers of sun-like stars, spiral together and erupt in titanic thermonuclear explosions that serve as the universe's standard candles. We will then descend into an even more extreme environment to see neutron stars, objects so dense, a teaspoon of their matter would weigh billions of tons, merge in a flash of light that forges the universe's precious metals and sends ripples through the very fabric of space-time. Finally, we will take our last and greatest leap in scale, zooming out to the realm of the galaxies, the grand cosmic cities that house the stars. Here, we will witness gravitational ballets played out over hundreds of millions of years as entire island universes, each containing hundreds of billions of suns, are drawn together in a slow-motion demolition. This dance of destruction ultimately builds the great cosmic structures of the future, from giant elliptical galaxies to the vast superclusters that trace the filaments of the cosmic web. This is our itinerary, a tour of the universe's most violent and creative moments. From the dust motes of our own solar system to the cosmic horizon, let us begin our journey. When you look at the night sky, you see the moon. It is a symbol of tranquility, a gentle, silent companion on Earth's long journey around the sun. Its soft silver light has inspired poets and lovers, guided travelers across dark oceans, and marked the passage of time for countless generations of humanity. We see it as a constant, a serene presence in a sky that is otherwise always changing. But this image of peace, this feeling of gentle familiarity, is a profound illusion. The moon is not a symbol of tranquility. It is a monument to cataclysm. It is a beautiful silent scar, a testament to the single most violent event in our planet's history, an event that nearly destroyed our world at its very birth. To truly understand the moon, we must reimagine it. We must strip away the poetry and the romance and see it for what it is, the ghost of a lost world born from a collision of unimaginable scale and fury. Our journey begins not in the sky, but on the ground. When the Apollo astronauts first walked on the moon, they did more than leave footprints. They collected rocks. These lunar samples were a scientific treasure trove, and they held a shocking secret. Chemically, the moon rocks were remarkably similar to the rocks of Earth's own mantle, yet subtly different. They were bone dry, lacking the volatile elements found on Earth, as if they had been subjected to immense heat. And they pointed to an origin story far more violent than anyone had imagined. The old theories that the moon was a captured asteroid, or that it had spun off from a rapidly rotating early Earth, could not explain this strange chemical fingerprint. The evidence pointed to a new radical idea, the giant impact hypothesis. This theory proposes that the moon was formed from the debris of a titanic collision between the young molten proto-Earth and another world. To understand this, we must travel back in time, back to the very dawn of the solar system some 4.5 billion years ago. This was not a time of serene, well-ordered orbits. It was a time of cosmic chaos, a gravitational shooting gallery, where dozens, perhaps hundreds of protoplanets were jostling for position around a young, fiery sun. The Earth was not yet the blue marble we know, but a molten hellish sphere constantly bombarded by debris. And it was not alone. In the darkness of the early solar system, another world was on a collision course with destiny. The serene face of the moon hides a secret, a story of a lost planet, and a collision that nearly tore our own world apart. Our story begins with a ghost, the ghost of a lost world. Astronomers have given this world a name steeped in mythology and fitting for the dramatic role it was destined to play. They call it Theia, after the mythical Greek Titaness, who was the mother of Selene, the goddess of the moon. This name is not just a poetic flourish. It is a recognition that our moon is the offspring of this ancient, vanished planet. What was Theia? Computer simulations, our only window into this deep past, suggest it was a world in its own right, a protoplanet roughly the size of modern-day Mars. It was born from the same swirling protoplanetary disk of gas and dust as the Earth, a cosmic sibling formed in the same neighborhood. For millions of years, the young Earth and Theia coexisted in a precarious gravitational harmony. They likely shared the same orbit around the Sun, locked in what is known as a Trojan configuration, with Theia trailing or leading the Earth by about 60 degrees. But in the intricate and chaotic dance of the early solar system, no harmony is eternal. The gravitational influence of other more distant planets, particularly the giants Jupiter and Venus, began to subtly perturb their orbits. It was like a gentle, persistent nudge, repeated over millions of years, slowly destabilizing their delicate balance. Theia began to drift from its stable Trojan point. Its orbit became more elongated, more eccentric. It began to wander. The two worlds born as neighbors were now set on a collision course. There was no malice, no intent. It was simply the inexorable, unfeeling logic of gravity playing out. The final act was set in motion, a slow-motion disaster that would unfold over centuries as their paths began to cross with increasing frequency. So how can we be so sure of this ghost planet's existence? The evidence is written in the chemistry of the moon. The Apollo samples revealed a strange isotopic similarity. The specific ratios of oxygen isotopes in the lunar rocks are almost identical to those on Earth, a unique chemical fingerprint. Yet, if the moon were a captured asteroid from some other part of the solar system, it should have a different isotopic signature. This points to a shared origin, a common source material. Furthermore, powerful supercomputer simulations that model the giant impact can only reproduce the Earth-Moon system as we see it today, with its specific mass, spin, and orbital characteristics, if the impacting object was roughly the size of Mars and struck the Earth with a glancing blow. The physics demands an impactor of a certain size and a certain type of collision. Theia is not just a convenient story. It is a scientific necessity, a ghost summoned by the evidence to explain the existence of our closest celestial companion. The tale of this lost world is the prologue to our own planet's story. Imagine the scene: a Mars-sized planet. Theia, its surface glowing a dull red with its own internal heat, looms in the sky of a young molten Earth. It is not falling from above like a meteorite. It is closing in on a converging path, a slow-motion disaster unfolding over hours, a silent waltz of gravitational inevitability. The collision, when it comes, is not a direct head-on impact. That would likely have shattered both worlds completely. Instead, Theia delivers a catastrophic glancing blow, sideswiping the proto-Earth at a velocity of over 40,000 kilometers per hour, 20 times faster than a speeding bullet. The energy released in this single moment is almost beyond human comprehension, equivalent to trillions of atomic bombs detonating at once. The impact liquefies and vaporizes rock on a planetary scale. In an instant, the world of Theia is obliterated. Its dense iron core, heavier than the surrounding rock, punches through the Earth's soft mantle and plunges deep into our planet's own core, merging with it and enriching our world with heavy metals. But Theia's lighter silicate mantle, along with a colossal amount of the Earth's own upper mantle, is blasted into space. This is not a simple explosion. It is a plume of superheated vaporized rock expanding outwards at incredible speed, a cosmic shotgun blast of planetary material. This debris does not escape Earth's gravity entirely. Instead, it enters orbit. For a time, our wounded planet, now deformed and superheated into a searing ball of magma, would have been surrounded by a brilliant glowing ring of incandescent rock and gas, a temporary and fiery version of Saturn's rings. The sound would have been non-existent in the vacuum of space, but the shockwave through the planet's body would have been apocalyptic. The entire globe would have rung like a bell, triggering earthquakes that would make any modern tremor seem like a faint vibration. The surface, a global ocean of magma, would have seen tidal waves of molten rock thousands of kilometers high. The Earth was nearly destroyed, its surface sterilized, its very shape distorted. The lost world of Theia was gone forever, its life as an independent planet extinguished in a fraction of a second. But its legacy, its very essence, was now captured in a fiery embrace orbiting the world it had almost annihilated. The stage was set for a new creation. In the aftermath of the Great Impact, a vast disk of superheated rock and gas, the combined remnants of Afor, Theia's obliterated mantle, and a significant portion of Earth's own crust now orbited our wounded planet. This was not a stable situation. Gravity, the same force that had orchestrated the collision, now became the architect of creation. Within this swirling incandescent debris disk, a remarkable process began. Tiny particles of dust and condensed rock vapor began to stick together, a process driven by both chemical bonds and their own minuscule gravitational attraction. These small clumps grew into larger ones, gathering more material as they swept through the disk. Small moonlets, perhaps kilometers across, began to form. This process is known as accretion, and it happened with astonishing speed. Imagine a gravitational snowball effect. As the largest of these moonlets grew, their own gravity became more powerful, allowing them to attract even more material at an ever-increasing rate. They began to clear their orbital paths, sweeping up the smaller debris. Computer simulations of this process suggest that the majority of the debris disk coalesced into a single large body in a remarkably short period of cosmic time, perhaps as little as a few decades, or at most a few centuries. A new world was born from the wreckage of two old ones. This was our moon, but this newborn companion was not the serene, pale orb we know today. Initially, it was a terrifying object, a molten ball of rock glowing a fierce, angry red, its surface a churning ocean of magma. And it was much, much closer to the Earth than it is now. If you could have stood on the surface of the primordial Earth, the moon would have appeared monstrous in the sky, perhaps 20 times larger than it does to us, a colossal fiery sphere dominating the heavens. Its proximity meant its gravitational influence on the Earth was immense. It raised colossal tides, not of water, but of molten rock sloshing across the surface of our planet. This constant gravitational kneading generated immense frictional heat within the Earth, likely contributing to keeping our world molten for longer and powering the vigorous geological activity like plate tectonics that would eventually shape our continents. The Great Impact was over, but its consequences embodied in this new fiery companion were just beginning to unfold. The collision was a moment of destruction, but the aftermath was an act of profound and beautiful creation. The Great Impact of Theia did more than just give Earth a beautiful companion in the night sky. It fundamentally reshaped our planet's destiny, transforming it from just another rock in space into a world uniquely suited for the emergence of life. The legacy of this ancient collision is written into the very fabric of our world, influencing everything from the length of our day to the rhythm of our seasons. Without this single violent event, the Earth we know today simply would not exist. First, consider the Earth's tilt. The glancing blow from Theia was not perfectly aligned with Earth's axis of rotation. The impact literally knocked our planet off kilter, giving it its characteristic 23.5-degree axial tilt. This tilt is the reason we have seasons. As the Earth orbits the Sun, different parts of the globe receive more direct sunlight at different times of the year, leading to the familiar cycle of spring, summer, autumn, and winter. Without this tilt, the equator would be perpetually scorched by a direct overhead sun, while the poles would be locked in an eternal frigid winter. The temperate zones where much of life and civilization flourishes would not exist. The diversity of climates and ecosystems on our planet is a direct consequence of this ancient shove. Furthermore, the presence of a large, close-orbiting moon provided a crucial stabilizing influence. Think of a spinning top. Left to its own devices, a top will wobble. The gravitational pulls of the Sun and giant planets like Jupiter exert a similar torque on the Earth, which would cause its axial tilt to wobble chaotically over long timescales, swinging between 0 and perhaps 85 degrees. This would lead to catastrophic and unpredictable climate swings, making it incredibly difficult for complex life to gain a foothold. But our large moon acts as a gravitational anchor, a steadying hand that dampens these wobbles and keeps Earth's tilt remarkably stable over billions of years. This climatic stability has been a vital prerequisite for the slow, steady process of evolution. The legacy of the collision is also felt in the length of our day. In the immediate aftermath of the impact, the Earth was spinning much, much faster, with a day that may have lasted only 5 or 6 hours. The newborn moon, orbiting much closer to the Earth, raised enormous tides on our planet's molten surface. This tidal bulge created a gravitational drag on the Earth, acting like a brake, and slowly, inexorably slowing its rotation over billions of years to the familiar 24 hours we know today. In a beautiful display of celestial symmetry, the energy lost by the Earth's spin was transferred to the moon's orbit, causing it to spiral slowly outwards, a journey it continues to this day, receding from us at a rate of about 3.8 centimeters per year. From the seasons that govern our agriculture to the very length of our day, the ghost of Theia is still with us. We live every moment in the world that this ancient world-shattering collision created. Let us now journey forward in time from the violent birth of our world to a day some 66 million years ago. We leave behind the molten primordial Earth and arrive on a planet that is almost unrecognizable in its tranquility and fecundity. This is the late Cretaceous period, the zenith of the age of reptiles. Our planet is a lush, vibrant greenhouse world, warmer and wetter than today. The continents have drifted into more familiar shapes, and vast, shallow seas cover much of what is now dry land. Life is abundant, diverse, and has been for over 150 million years. This is a world ruled by giants. Imagine the scene. In the great cypress swamps and fern-covered plains of what will one day be North America, a Tyrannosaurus rex, the apex predator of its time, stalks its prey. Herds of armored triceratops, each weighing as much as a modern elephant, graze peacefully. The skies are not filled with birds, but with giant pterosaurs like Quetzalcoatlus, with wingspans as wide as a fighter jet. The warm oceans teem with life, from coiled ammonites to giant predatory mosasaurs, the T-Rex of the deep. This is a stable, mature ecosystem, a world that seems permanent, timeless. On this particular day, the sun rises on a planet that knows nothing of its impending doom. The air is warm, the forests are quiet, and life continues its ancient, unhurried rhythm. It is a day like any other in a reign that has lasted for an incomprehensible length of time. But far out in the cold darkness of space, on a trajectory calculated by the unfeeling laws of celestial mechanics, millions of years earlier, an object is closing in. It is a cosmic bullet, an asteroid, or perhaps a comet roughly 10 kilometers in diameter. Imagine taking a mountain like Everest and launching it into space. This is the scale of the object. It has been traveling on a long elliptical orbit around the sun, and by sheer cosmic chance, its path is about to intersect with Earth's. There is no warning. For the creatures on the ground, the sky is clear and peaceful. There is no sense of foreboding, no sign of the serene apocalypse that is just moments away. In a single catastrophic instant, a random encounter in the vastness of the solar system, is about to end an entire geological era and rewrite the future of life on Earth. The long, peaceful reign of the dinosaurs is about to come to a sudden and fiery end. It enters the Earth's atmosphere at a velocity of at least 20 kilometers per second, a mountain of rock and ice moving 20 times faster than a rifle bullet. It compresses the air in front of it into a superheated plasma hotter than the surface of the sun. In the final terrifying seconds, it would have appeared as a new, impossibly bright star in the daytime sky, growing in intensity until it outshone the sun itself, a silent harbinger of doom. It strikes at a steep angle in the shallow tropical seas of what is now the Yucatan Peninsula, in a place we have come to call Chicxulub. The impact is a hammer blow of cosmic proportions. The energy released is almost indescribable, equivalent to over 100 trillion tons of TNT, or billions of atomic bombs, all detonating in a single catastrophic instant. The asteroid itself, along with a huge volume of the Earth's crust beneath it, is vaporized in less than a second. The impact carves out a transient crater over 100 kilometers wide and 30 kilometers deep, punching a temporary hole through the Earth's crust and into the mantle below. The initial blast sends a titanic shockwave outwards through the planet's crust, triggering earthquakes of magnitude 11 or greater across the globe, a seismic event of a scale that dwarfs anything in human history. It launches a colossal plume of superheated rock ash and vaporized asteroid high above the atmosphere, sending it into suborbital trajectories around the globe. This material, on its fiery return journey, rains down across the entire planet as trillions of incandescent glass beads known as tektites. This rain of fire heats the upper atmosphere to oven-like temperatures, perhaps several hundred degrees Celsius, and ignites massive global wildfires. Any creature on the surface that could not find shelter underground or underwater was incinerated within hours. But the horror was just beginning. The impact generated a mega tsunami of biblical proportions. A wall of water perhaps over a kilometer high radiated outwards from the impact site, scouring the coastlines of the ancient Gulf of Mexico and traveling deep into the interior of continents. The sky turned black with soot and debris. The immediate aftermath of the Chicxulub impact was an apocalypse of fire, earthquake, and flood, a planetary-scale event that sterilized a vast portion of the globe in a matter of hours. The serene Cretaceous day had ended in a vision of hell, but the true world-ending consequence of the impact was yet to come. The hammer blow had fallen, but the long, dark winter was just beginning. The immediate fires and floods of the Chicxulub impact were only the opening act of the apocalypse. The truly world-ending consequence, the blow that would bring an entire geological era to its knees, was what the impact threw into the atmosphere. The impact site in the Yucatan Peninsula was geologically unique. The bedrock was rich in sulfur-bearing minerals like gypsum and in carbonates. The colossal energy of the collision vaporized these rocks, injecting hundreds of billions of tons of sulfur aerosols, soot from the global wildfires, and pulverized rock dust high into the stratosphere. This was not like the ash from a volcanic eruption, which washes out of the lower atmosphere in a matter of weeks. Material injected into the stratosphere can linger for years, even decades. This material formed a thick global shroud that blocked out the sunlight. The Earth was plunged into a deep, dark twilight that lasted for years, a nuclear winter without the nuclear bomb, an impact winter. Photosynthesis, the fundamental process that powers almost all life on Earth, ground to a halt. On land and in the oceans, the base of the food chain collapsed. The lush forests and fern prairies of the Cretaceous withered and died in the prolonged darkness and cold. The great herds of herbivorous dinosaurs that fed on them starved by the millions. and the giant carnivores like Tyrannosaurus rex that hunted the herbivores soon followed. The intricate web of life woven over 150 million years was unraveling from the bottom up. The oceans, which had been warm tropical seas, suffered a similar fate. The vast quantities of sulfur in the atmosphere mixed with water vapor to form sulfuric acid, which then fell back to Earth as a planet-wide acid rain. The surface layers of the oceans became dangerously acidified. This dissolved the delicate calcium carbonate shells of countless marine organisms, from the tiny plankton that formed the base of the marine food web to the great coiled ammonites that had dominated the seas for eons. The collapse was swift and total. When the dust finally settled and the sunlight returned to a scarred and broken world, the planet was eerily quiet. More than 75% of all species on Earth had been wiped out. All non-avian dinosaurs, the giant marine reptiles, the pterosaurs in the sky, all gone. The long, seemingly invincible reign of the dinosaurs was overended not by a gradual decline or a failure to adapt, but by a single catastrophic blow from the cosmos. An era had ended, and the stage was now set for the rise of a new kind of life, the small, resilient mammals that had survived the long winter by hiding in the shadows. The story of the Chicxulub impact carries a chilling and deeply personal message. What has happened before can happen again. The solar system is still a shooting gallery filled with millions of asteroids and comets, the leftover rocky and icy debris from its formation 4.6 billion years ago. While the odds of an impact on the scale of the dinosaur killer are thankfully slim in any given century, they are not zero. Over geological timescales, they are a certainty. But there is a profound difference between our world and the world of the dinosaurs. For the first time in our planet's long and often violent history, a species has arisen that has the capacity to understand this threat and potentially to do something about it. We are the universe's way of defending itself. This is the new and exciting field of planetary defense. This cosmic watch is not science fiction. It is a global, ongoing effort. Astronomers across the globe operate a network of ground-based and space-based telescope systems like the Catalina Sky Survey in Arizona, Pan-STARRS in Hawaii, and NASA's NEOWISE space telescope. Night after night, they systematically scan the skies, taking rapid sequences of images of the same patch of sky. By comparing these images, computer algorithms can detect the faint points of light that have moved against the background of fixed stars. These are the near-Earth objects, or NEOs. Once detected, their positions are tracked, and their orbits are calculated with high precision, allowing us to predict their paths for decades, even centuries into the future. To date, we have found over 95% of the kilometer-sized civilization-ending asteroids, and thankfully none poses a significant threat for the foreseeable future. But watching is not enough. What do we do if we find one on a collision course? In a landmark mission that feels like it was pulled from a Hollywood script, NASA gave us the beginning of an answer. On November 24, 2021, the Double Asteroid Redirection Test, or DART mission, was launched. Its target was a small asteroid moonlet named Dimorphos, orbiting a larger asteroid called Didymos, hundreds of millions of kilometers from Earth. The goal was simple, yet audacious, to deliberately crash a refrigerator-sized spacecraft into Dimorphos at high speed and see if we could change its orbit. On September 26, 2022, DART slammed into its target at 22,500 kilometers per hour. The result was a spectacular success, exceeding all expectations. The impact not only nudged the asteroid, but also blasted out a huge plume of debris, which acted like a rocket thruster, amplifying the effect. The orbital period of Dimorphos was shortened by a full 32 minutes, proving that this kinetic impactor technique is a viable strategy for planetary defense. We are no longer passive victims of cosmic chance. We have become the guardians of our world, keeping a vigilant watch on the darkness between the worlds. The success of the DART mission is a triumph of human ingenuity, a powerful symbol of our transition from passive observers to active participants in our own cosmic destiny. We have built a shield, a network of watchful eyes, and a nascent ability to nudge cosmic bullets aside. But this newfound capability brings with it a sobering sense of responsibility and a new set of unanswered and perhaps unanswerable questions. Our planetary defense system is a remarkable achievement, but it is far from foolproof. Have we truly made our world safe? We have cataloged nearly all of the civilization-ending asteroids of a kilometer or more in size, the dinosaur killers, and can say with a high degree of confidence that none poses a threat for at least the next century. But our solar system is vast, and the darkness holds many secrets. What of the smaller city-killer asteroids, those tens to hundreds of meters across? They are far more numerous and much harder to detect, yet they still pack enough energy to obliterate a major metropolitan area. Our surveys have found only a fraction of them. An impact from one of these objects is a low probability but high consequence event, a game of cosmic roulette we are forced to play every day. And what of the objects that come from the deep freeze? The long-period comets, great mountains of ice and rock that fall in from the Oort cloud, the outermost frontier of our solar system 1 trillion kilometers away. These objects travel on orbits that take thousands or even millions of years to complete. We would have very little warning of their approach, perhaps only months, as they swing in towards the sun and begin to brighten. The DART mission was a triumph, but it was a carefully planned test against a tiny known target. Could we successfully mount a defense against a larger, faster-moving comet discovered only a year before impact? Do we have the technology, the resources, and the international political will to act decisively on such short notice? We have built our civilizations on a planet that we perceive as a safe, stable haven. But the stories of Theia and Setimo Chicxulub remind us that this stability is a fragile illusion, a temporary truce in a long cosmic war. We are a species that has finally learned to look up and understand the danger. The lingering, unanswered question remains: have we learned enough? And have we acted in time? Or are we like the dinosaurs, simply enjoying a moment of serene calm before the next inevitable hammer blow falls from the sky? Our haven is beautiful, but it is fragile, and the universe is not finished with it yet. Leaving our solar system behind, our journey now takes us into the vaster, more dynamic arena of the galaxy itself. Here, we encounter collisions on a stellar scale, a dance of suns that is both more subtle and, in some cases, far more violent than the planetary impacts we have explored. Our Sun is just one of some 200 billion stars in the Milky Way, all bound together by gravity, all orbiting the galactic center in a majestic slow-motion swirl that takes over 200 million years to complete. From our perspective on Earth, the stars seem like fixed, isolated points of light, separated by unimaginable gulfs of empty space. And for the most part, this is true. The average distance between stars in our galactic neighborhood is so vast that a direct head-on collision between two stars is an exceptionally rare event, something that might happen only once every 10,000 years in the entire galaxy. Space, it turns out, is mostly space. But the galaxy is not a perfectly ordered dance. It is a crowded, chaotic place, especially in its heart, and in the dense stellar nurseries where stars are born. Stars are not born in isolation. They are born in great clusters from hundreds to millions of stars, all formed from the same giant cloud of gas and dust. Within these dense environments, gravitational interactions are common and complex. Imagine a cosmic game of billiards where the balls are suns. In this intricate dance, a star can be gravitationally nudged, its orbit altered, or it can be ejected from the cluster entirely sent careening through the galaxy as a rogue sun. Our own sun was likely born in such a cluster and may have had its own close encounters with its siblings in the distant past, before being cast out into its current, more solitary existence. And a star does not need to physically collide with a solar system to wreak havoc. A close pass, a gravitational sideswipe, is all it takes to disrupt the delicate, stable orbits of planets that have been in place for billions of years. Imagine a rogue star passing through the Oort cloud of a system like our own. Its gravitational pull would be like a hand plunging into a beehive, sending a devastating shower of comets careening towards the inner solar system, triggering an era of constant bombardment. A closer pass could directly perturb the orbits of the planets themselves, sending a world like Earth into a new frigid orbit far from its sun, or worse, plunging it into the fiery heart of its own star. The dance of suns is a subtle one, but its consequences can be just as deadly as any direct impact. In the stellar realm, gravity's influence is absolute, and its consequences tyrannical. When two or more stars pass close to one another, their gravitational fields interact in a complex and often violent exchange of energy and momentum. This is the principle of the gravitational slingshot, a technique our own space probes like the Voyager missions have used to accelerate towards the outer planets. A spacecraft cleverly steals a tiny amount of a planet's immense orbital energy to boost its own speed, flinging it onward to its next destination. When stars interact, the same physics applies, but on a terrifyingly larger and more chaotic scale. A close encounter can fundamentally and irrevocably alter the destinies of stars and any planets that may orbit them. In a dense star cluster, a smaller, faster-moving star can have a close encounter with a more massive binary star system. In this three-body dance, the smaller star can be captured ejecting one of the original binary partners with tremendous force. The result is a hypervelocity star, a sun flung out of its home cluster at incredible speeds, sometimes exceeding 1,000 kilometers per second, fast enough to eventually escape the gravity of the Milky Way itself. These stellar cannonballs are destined to travel the lonely, dark voids between the galaxies, a testament to the chaotic dynamics of their birthplaces. But what about the planets caught in the crossfire? In a planetary system, the consequences of a stellar flyby are even more dire. The delicate gravitational balance that keeps planets in stable, predictable orbits can be easily shattered. Imagine a rogue star, a wandering sun ejected from its own birth cluster, passing through a mature solar system. Its gravitational influence would be like a wrecking ball. The system's asteroid and comet belts would be thrown into disarray, unleashing a devastating, prolonged bombardment on the inner planets, a celestial winter that could last for millions of years. But the tyranny of gravity can be even more direct. A close pass can directly perturb the orbit of a planet itself. A world like Earth could be pulled from its gentle circular orbit in the habitable zone and flung into a new, highly elliptical path, subjecting it to wild swings in temperature from scorching summers to deep frozen winters. Or worse, it could be ejected entirely stripped from its parent star and condemned to an eternity of cosmic exile. This is not science fiction. Astronomers have discovered a population of these rogue planets, dark, silent worlds drifting forever through the cold and empty space between the stars' ghost worlds that are a chilling monument to the tyranny of gravity. Let us paint a picture of such a stellar encounter, a story of cosmic exile. Imagine a quiet, stable solar system much like our own, orbiting a sun-like star. On one of its planets, a world nestled in the gentle warmth of the habitable zone, life has taken hold. For billions of years, it has known nothing but the steady, life-giving light of its parent star. Its oceans teem with complex organisms, and its continents are green with a strange and alien form of vegetation. It is a world in its prime, a vibrant oasis in the cosmic desert. But in the galactic dark, a planet killer approaches. It is a rogue star, perhaps a cool, dim red dwarf ejected from its own birth cluster eons ago, now wandering the galaxy like a silent predator. As it enters the system, it appears as a new, ominous red star in the sky, a baleful eye growing steadily brighter, with each passing year a harbinger of the chaos to come. The orbits of the outer gas giant planets begin to warp and shift under its gravitational influence. The system's asteroid belt is thrown into disarray, unleashing a devastating bombardment on the inner planets. The sky of our living world is now filled with fire, a constant rain of death from above. The climate collapses, and the great extinction has already begun. Then the red dwarf makes its closest approach, passing just inside the orbit of the life-bearing planet. The gravitational tug is immense. The planet is pulled from its gentle circular orbit and flung outwards like a stone from a cosmic sling. It is not destroyed, but it is exiled. As it recedes from the warmth of its sun, its oceans begin to freeze from the poles downwards until the entire world is encased in a shell of ice kilometers thick. Its atmosphere collapses, snowing down onto the frozen surface. Any life that survived the bombardment is now entombed in eternal darkness and cold. The planet is now a rogue, a dark and silent tomb, its vibrant biosphere reduced to a frozen fossil record. It is a stark and brutal illustration of the fact that in the galaxy, no home is truly safe, and even a sun can become a planet killer. This story of cosmic exile is a reminder that stability is a precious and perhaps temporary gift. The most spectacular stellar collisions often involve not living, breathing stars, but their corpses. Our journey now takes us into the stellar graveyard, a realm of cosmic embers, ghosts, and zombies, where the universe's most extreme physics is on full display. When a star like our Sun, a relatively modest star, runs out of hydrogen fuel in its core, it doesn't explode in a violent supernova. Instead, it swells up into a red giant, engulfing its inner planets. Then, over thousands of years, it gently puffs off its outer layers to form a beautiful, intricate structure known as a planetary nebula. What is left behind at the center is the hot, dense, and dying core of the former star. This is a white dwarf. A white dwarf is an object of incredible density, a cosmic ember with the mass of our Sun crushed into a volume the size of the Earth. They are the ghosts of stars that once were. But the story doesn't end there. Most stars are not born alone. They are born in binary pairs, locked in a gravitational dance that will continue even after they die. Imagine a system where two stars born together have both exhausted their fuel and become white dwarfs. They are two stellar corpses orbiting each other in the silent darkness, a testament to a once brilliant past. For millions, perhaps billions of years, their ghostly dance is stable. But their story cannot end in peace. It is doomed by the predictions of Einstein's general theory of relativity. As these two incredibly dense objects whirl around each other, they are constantly and violently stirring the very fabric of spacetime, creating ripples that spread outwards at the speed of light. These are gravitational waves. These waves are not just a theoretical curiosity, they are a physical reality, and they carry energy away from the binary system. It is a slow but inexorable process. As the system loses orbital energy, the two white dwarfs spiral closer and closer together. Their orbital speed increases, which in turn causes them to radiate gravitational waves, even more powerfully accelerating the process in a feedback loop of doom. The dance quickens. What began as a sedate billion-year waltz becomes a frantic final pirouette. In the last few minutes of their existence, the two Earth-sized stellar cores are orbiting each other thousands of times per second. The immense tidal forces of their mutual gravity distort their shapes from perfect spheres into elongated teardrops, their tips reaching out towards one another. They are about to merge, and in doing so, they will ignite a fire that has been dormant for eons, a final spectacular act of stellar violence that will be visible across half the universe. This dance of two ghosts is not just a cosmic curiosity. It is the prelude to one of the most important and powerful types of explosion in the entire cosmos. The final violent merger of two white dwarfs is an instantaneous and catastrophic event. The combined mass of the new oversized object exceeds a critical threshold, a tipping point in cosmic physics, known as the Chandrasekhar limit. This limit, named after the brilliant Indian-American astrophysicist Subramanian Chandrasekhar, represents the absolute maximum mass, about 1.4 times that of our Sun, that can be supported by the quantum mechanical force called electron degeneracy pressure. Once this limit is breached, gravity wins. The core of the merged object collapses inward under its own weight, and in a fraction of a second, runaway carbon fusion ignites throughout the entire stellar remnant. The result is not a gentle puff, but a titanic thermonuclear explosion that utterly annihilates the star. This is a Type Ia supernova. But this explosion is more than just a spectacular stellar death. It is one of the most important tools in all of cosmology, because all Type Ia supernovae are triggered when a white dwarf crosses the same precise mass limit. They all explode with almost exactly the same intrinsic brightness, the same absolute luminosity. They are, in effect, standard candles. Imagine you are in a vast dark field at night, and someone lights a series of identical 100-watt light bulbs at various distances. By measuring how faint each bulb appears to you, you can accurately calculate how far away it is. A bulb that appears 4 times fainter is twice as far away. Type Ia supernovae are the universe's 100-watt light bulbs. They are so incredibly bright that they can be seen across billions of light-years, briefly outshining their entire host galaxies. When astronomers spot one of these explosions in a distant galaxy, they can measure its apparent brightness. By comparing this to its known standard intrinsic brightness, they can calculate the distance to that galaxy with incredible precision. These ghostly collisions born from the death dance of long-dead stars have become the lighthouses of the cosmos. They are the cosmic yardsticks we use to measure the vast, otherwise incomprehensible distances to other galaxies, and in doing so, they allow us to map the structure and evolution of the universe itself. The final violent act of two stellar ghosts provides the light that illuminates the grandest scales of reality. So how do we know how far away a distant galaxy is? We cannot stretch a cosmic tape measure across millions of light-years. The answer lies in one of the most elegant and ingenious constructions in all of science, the cosmic distance ladder. It is a series of overlapping techniques, each one building on the last, allowing us to step further and further out into the universe. The first rung of the ladder is the most direct stellar parallax. As the Earth orbits the Sun, nearby stars appear to shift their position slightly against the background of more distant stars. By measuring this tiny angular shift and knowing the diameter of Earth's orbit, we can use simple trigonometry to calculate the star's distance. This method is the gold standard, but it only works for our closest stellar neighbors out to a few thousand light-years. To go further, we need to climb to the next rung. This is where a special type of pulsating star called a Cepheid variable comes in. In the early 20th century, an astronomer at the Harvard College Observatory named Henrietta Swan Leavitt made a remarkable discovery. While studying these variable stars, she found a direct, precise relationship between the period of their pulsations and their true intrinsic brightness. The longer it took for a Cepheid to pulse, the more luminous it was. This was a breakthrough. Cepheids became a new kind of standard candle. If you can measure the pulsation period of a distant Cepheid, you know its true brightness. By comparing that to its apparent brightness in the sky, you can calculate its distance. This allowed us to measure distances across our entire Milky Way, and even to our nearest galactic neighbors, like Andromeda. But to reach the truly distant galaxies billions of light-years away, we need something much, much brighter than a single star. We need the final highest rung on our ladder. This is the crucial role played by the type Ia supernova. These exploding white dwarfs are so astonishingly bright that they can be seen from the very edge of the observable universe. By finding Cepheid variables in a relatively nearby galaxy that has also hosted a type Ia supernova, we can use the Cepheids to get a precise distance to that galaxy. This in turn allows us to calibrate the exact standard brightness of the supernova itself. Once calibrated, we can spot these spectacular explosions in the most distant reaches of the cosmos and use them to measure the unmeasurable. It was by using these colliding stellar ghosts as cosmic lighthouses that astronomers in the late 1990s made one of the most shocking and profound discoveries in the history of science. The expansion of the universe is not slowing down under the pull of gravity, as everyone had expected. It is accelerating, driven by a mysterious, repulsive force we now call dark energy. The ghosts of dead stars revealed the universe's ultimate and unexpected fate. If a white dwarf is a star's ghost, then our next subject is its zombie. We are now entering the realm of one of the most extreme and bizarre objects in the entire universe, the neutron star. These are the stellar remnants left behind by much more massive stars, those born with between 8 and 20 times the mass of our Sun. When these giants die, they don't fade away quietly. They explode in a spectacular core collapse supernova, an event that for a brief time can outshine its entire galaxy. But unlike a type Ia supernova that leaves nothing behind, this explosion leaves a corpse, and what a corpse it is. During the star's final collapse, the core is crushed with such ferocious, overwhelming force that gravity overcomes the electron degeneracy pressure that supports a white dwarf. In the star's heart, protons and electrons are literally squeezed together to form a ball of pure neutrons packed together as tightly as the particles in an atomic nucleus. The result is an object of almost unimaginable density. A neutron star has more mass than our Sun, but it is compressed into a sphere only about 20 kilometers in diameter, roughly the size of a single city like Manhattan. To grasp this, imagine taking a mountain like Everest and compressing it down to the size of a sugar cube. The result would still be 1,000 times less dense than a neutron star. A single teaspoon of neutron star matter would weigh 10 million tons, as much as a fleet of battleships. They are the densest objects in the known universe, short of a black hole itself. But their extreme nature doesn't end there. As the massive star's core collapses, its rotation speed increases dramatically, due to the conservation of angular momentum, the same principle that causes a spinning ice skater to speed up when they pull their arms in. A newborn neutron star can spin at incredible speeds, often hundreds of times per second. This rapid rotation, combined with the star's original magnetic field, which is also compressed and amplified to an incredible degree, turns the neutron star into a cosmic dynamo. They possess magnetic fields trillions of times stronger than Earth's, the most powerful magnetic fields in the universe. They are stellar zombies, fantastically dense, rapidly spinning, and magnetically potent. And just like their ghostly white dwarf cousins, they are often found in pairs, setting the stage for a collision of even more epic and universe-altering proportions. Just like their less dense white dwarf cousins, a pair of orbiting neutron stars is doomed to spiral inwards, losing energy through the ceaseless emission of gravitational waves. But because neutron stars are so much more massive and orbit each other so much more closely, the gravitational waves they produce are far more powerful. As they whirl around each other at a significant fraction of the speed of light, they are not just stirring space-time. They are violently churning it, sending a powerful crescendo of ripples outwards through the cosmos. For a century, these waves were just a prediction of Einstein's theory. But what if we could hear them? What if we could build an instrument sensitive enough to detect these faint cosmic vibrations? This was the audacious goal of the Laser Interferometer Gravitational Wave Observatory, or LIGO. Imagine building the most sensitive microphone in human history, designed not to hear sound, but to listen to the ringing of space-time itself. This is LIGO. It consists of two enormous L-shaped detectors, one in the forests of Livingston, Louisiana, and the other in the high desert of Hanford, Washington, separated by 3,000 kilometers to rule out local vibrations. Each arm of the L is a 4-kilometer-long vacuum tunnel, the straightest and emptiest corridors on Earth. At the corner, a powerful laser is split into two beams, which are sent down each arm. They reflect off perfectly polished mirrors at the end and return to the corner where they are recombined. If the arms are exactly the same length, the two light waves should cancel each other out perfectly. But when a gravitational wave from a distant cosmic cataclysm passes through the Earth, it stretches one arm and squeezes the other by an infinitesimal amount, a distance less than 1/10,000th the diameter of a proton. But LIGO's incredibly sensitive detectors can measure this tiny distortion, allowing us to listen in on the symphony of the universe's most violent events. On August 17, 2017, it happened. For about 100 seconds, LIGO and its European partner Virgo listened to the telltale chirp of two inspiraling neutron stars. The detectors tracked the gravitational waves as they increased in frequency and amplitude, the signature sound of two stellar zombies spiraling towards their final cataclysmic collision in a galaxy 130 million light-years away. Then the signal abruptly stopped. The stars had merged. At that exact moment, just 1.7 seconds later, NASA's Fermi Gamma Ray Space Telescope detected a brief 2-second flash of high-energy light from the same patch of sky. For the first time in history, we had both seen and heard the same cosmic event. An urgent alert was sent out to observatories around the globe. The gravitational wave symphony had given us a front-row seat to the birth of a kilonova. In the hours and days following the gravitational wave and gamma-ray burst signals from the event now known as GW1 70817, telescopes all over the world scrambled to point at the source galaxy, NGC 4993. What they saw was something new, a celestial transient predicted by theory, but never before observed with such clarity, a kilonova. This is the explosion that results from the merger of two neutron stars. It is less bright than a typical supernova, perhaps only 1,000 times brighter than a standard nova, hence the name kilonova, but it is powered by a completely different and far more exotic process, the radioactive decay of heavy elements freshly synthesized in the collision. The merger itself is an event of unimaginable violence. As the two city-sized stellar zombies collide at 1/3 of the speed of light, their neutron-rich matter is shredded and flung out into space in a chaotic, expanding cloud. The temperatures and densities in this debris cloud are extreme, creating the perfect conditions for a process known as the IR process, or rapid neutron capture. In this cosmic pressure, cooker-existing atomic nuclei are furiously bombarded with a dense sea of free neutrons. They absorb neutron after neutron, rapidly growing into the heaviest and rarest elements in the universe before they have time to radioactively decay. All the gold in your wedding ring, the platinum in a catalytic converter, the iodine that regulates your thyroid, and the uranium that powers a nuclear reactor, every single atom of these precious and heavy elements was created in the cataclysmic seconds-long forge of a neutron star collision. As these newly minted radioactive elements decay, they release energy causing the expanding cloud of debris to glow. But the light it emits tells a story. In the first few days, the kilonova shone with a bright blue light, the signature of lighter R process elements. Then, over the following weeks, it faded and reddened as the slower decaying heavier elements like gold and platinum began to dominate the light signature. By analyzing the changing colors of this fading afterglow, astronomers could see the chemical fingerprints of the universe's treasures being forged in real time. The collision, which occurred 130 million years ago, is estimated to have produced an amount of gold equivalent to several times the entire mass of the Earth, along with even larger quantities of platinum and other heavy metals. These cosmic riches were then blasted out into the interstellar medium, seeding the galaxy with the raw materials for future generations of stars, planets, and perhaps life. The most violent collisions are the universe's most generous benefactors. The familiar and poetic phrase, "we are made of stardust," is more than just a beautiful sentiment. It is a profound and literal scientific truth. But the story of our cosmic origins is richer and more violent than that simple phrase implies. The Big Bang itself created only the lightest elements, hydrogen, helium, and a trace amount of lithium. Every other element on the periodic table, every atom that makes up our world and our bodies, had to be forged in the fiery hearts. The familiar and poetic phrase, "we are made of stardust," is more than just a beautiful sentiment. It is a profound and literal scientific truth. But the story of our cosmic origins is richer and more violent than that simple phrase implies. The Big Bang itself created only the lightest elements, hydrogen, helium, and a trace amount of lithium. Every other element on the periodic table, every atom that makes up our world and our bodies, had to be forged in the fiery hearts of stars and scattered by their cataclysmic deaths. The carbon in our DNA, the nitrogen in our atmosphere, the oxygen we breathe, these were created by nuclear fusion inside stars like our Sun, and gently puffed out into space in planetary nebulae. The heavier elements, like the silicon in the rocks beneath our feet and the iron in our blood, were forged in the final explosive moments of massive stars going supernova. But what about the heaviest, rarest elements? What about gold, platinum, and uranium? For decades, their origin was a mystery. Supernovae could not account for the sheer abundance of these elements in the cosmos. The answer we now know comes from an even more violent and exotic cosmic forge. The event GW 170817 The first observed merger of two neutron stars provided the final definitive proof. The light from its kilonova afterglow contained the clear chemical fingerprints of these heavy elements being created in vast quantities. It confirmed that these spectacular collisions are the universe's primary source for its greatest treasures. The next time you hold a piece of gold jewelry, remember where it came from. Its atoms were not born on Earth. They were forged 130 million years ago in the cataclysmic seconds-long collision of two city-sized stellar zombies, and then journeyed across interstellar space for eons to become part of the dust cloud that would one day form our solar system. We are not just made of stardust. We are made of the wreckage of cosmic collisions, the children of the universe's most violent and creative acts. What is left behind after two neutron stars merge and the brief, brilliant light of the kilonova fades. The aftermath is as profound as the collision itself. The combined object, now containing the mass of nearly 3 suns, is far too massive to be supported by neutron degeneracy pressure. For a brief, fleeting moment, it may form a hypermassive neutron star, a bizarre, rapidly spinning object stabilized only by its own incredible rotation. But this stability is temporary. As it inevitably spins down, it is doomed to collapse under its own colossal weight. Gravity wins. The final remnant of a neutron star merger is a newborn monster, a stellar mass black hole. A point of infinite density, a singularity is born from the wreckage cloaked by an event horizon from which nothing, not even light, can ever escape. The collision of two of the densest objects in the universe creates the ultimate object of density. This process represents a key pathway for the formation of stellar mass black holes, particularly those that might be slightly more massive than the ones formed from the collapse of a single isolated star. The violent kilonova explosion fades the precious heavy elements it created, disperse into the void to enrich the galaxy, and what remains is a silent, invisible tear in the fabric of space-time. A permanent monument to the cataclysm that created it. This birth of a black hole sets the stage for the final and most extreme type of stellar-scale collision, one that is utterly invisible to any telescope that sees in any form of light. This is the merger of two stellar mass black holes themselves. These are the dark remnants of the most massive stars in the universe, or the newborn monsters from previous neutron star mergers. Like their stellar zombie cousins, they are often found in binary systems, locked in a gravitational dance of pure darkness. As they orbit each other, they too radiate gravitational waves, lose orbital energy, and spiral inexorably inwards. But unlike a neutron star merger, there is no brilliant explosion of light, no kilonova to announce the final union. There is no matter to be flung out, no elements to be forged. There is only a final silent and complete merger of two patches of absolute darkness. The two event horizons touch, distort, and coalesce, settling down into a single, larger and more massive black hole in a process called ringdown. The only evidence of this event, the only sound it makes, is a powerful final burst of pure gravitational wave energy. The energy released in these final milliseconds is staggering. For a fraction of a second, the merger of two black holes can radiate more raw energy in the form of gravitational waves than all the hundreds of billions of stars in the observable universe combined. It is the most powerful event in the universe since the Big Bang itself, and it happens in complete and total darkness. For a century, humanity stared out at the universe blind to its most violent and powerful events. We were like a deaf person at a symphony, able to see the musicians, but unable to hear the music. We could see the light from stars and galaxies, But we were completely deaf to the vibrations of space-time itself. All of that changed on September 14, 2015. At 9:50:45 Coordinated Universal Time, a ripple in the fabric of reality created by a cataclysmic event in a distant galaxy washed over the Earth. It passed through our planet and us as if we weren't there. But two extraordinary instruments, the twin detectors of LIGO, were listening. For a fleeting fifth of a second, their lasers registered a signal of almost impossible subtlety. It was a clear, unambiguous chirp, the sound of space-time ringing, sweeping up in frequency and amplitude before abruptly stopping. This signal, named GW15500914, was the universe's first song, and it told a dramatic story. It was the sound of two stellar mass black holes, one about 36 times the mass of our Sun, and the other about 29 times, that had been locked in a gravitational death dance for billions of years. The chirp was the sound of their final moments as they spiraled together at nearly half the speed of light and merged into a single larger black hole of about 62 solar masses. What happened to the missing 3 solar masses? They were not lost. They were converted in a fraction of a second directly into the raw energy of gravitational waves, according to Einstein's famous equation, E = mc2. The energy released was staggering, more than 50 times greater than the combined light output of all the stars in the observable universe. This event had happened 1.3 billion years ago, in a galaxy 1.3 billion light-years away, when the most complex life on Earth was still single-celled algae. The waves had been traveling towards us ever since. This was a monumental moment in the history of science, a discovery that would win the Nobel Prize in Physics just 2 years later. It was the first direct detection of gravitational waves, a stunning confirmation of a century-old prediction of Einstein's theory of general relativity. But it was so much more than that. It was the dawn of a new era in astronomy. For the first time, we were not just seeing the universe, we were listening to it. We had developed a completely new sense with which to perceive the cosmos, a sense that is blind to light, but exquisitely sensitive to the vibrations of gravity. We had finally opened a new window onto the dark, hidden, and most violent side of the universe. The symphony was just beginning. Since that first faint song from a distant galaxy, the twin detectors of LIGO and their European partner Virgo have opened the floodgates. Dozens of these cosmic mergers have now been detected, and a new catalog of the universe's most violent events is being written. We have heard the symphony of black holes colliding with other black holes, allowing us to map the unseen population of these stellar ghosts. We have heard the dramatic crescendo of neutron stars merging with neutron stars, providing a cosmic laboratory to study the physics of matter at its most extreme densities. And we have even detected the exotic and previously only theoretical collision of a black hole with a neutron star, an event where the unfortunate stellar zombie is likely shredded and swallowed whole in a final brutal act of cosmic vampirism. Each new detection is a new note in the cosmic symphony, a new piece of a puzzle that is revolutionizing our understanding of the universe. By carefully analyzing the precise shape of the gravitational waveform, the sound of the collision, we can deduce an incredible amount of information. We can determine the precise masses of the colliding objects, whether they were spinning, and how fast their distance from us, and even their orientation in the sky. This new field of multi-messenger astronomy, where we combine the information from gravitational waves with observations from traditional light-based telescopes, is allowing us to probe the universe in ways that were previously impossible. We are creating a census of black holes, testing the absolute limits of Einstein's general relativity in the most extreme environments imaginable, and learning about the life, death, and violent afterlives of the universe's most massive stars. The legacy of these invisible collisions is a new era of discovery, a new sense with which to experience reality. For millennia, our entire understanding of the cosmos came through the narrow window of the electromagnetic spectrum. Visible light radio waves, X-rays. It was as if we were trying to understand an entire orchestra by only listening to the violins. Now, with gravitational waves, we can hear the percussion section. We can hear the deep, resonant bass notes of the universe's most massive and violent events that are completely dark and silent to all our other instruments. The legacy of listening is a more complete, more visceral, and ultimately more truthful picture of the universe. A universe that is far more chaotic, violent, and creative than we ever dared to imagine. Our journey now takes another dramatic leap in scale, moving beyond the violent lives and deaths of individual stars to the vast cosmic cities they inhabit, the galaxies. If stars are the citizens of the universe, then galaxies are its great nations, sprawling empires of light and gravity. Our Milky Way is a majestic spiral galaxy, a spinning disk of some 200 billion stars, gas and dust stretching 100,000 light-years from end to end. From our vantage point, on a small rocky planet in one of its quiet suburbs, it seems like a solitary island of light in the vast, dark ocean of intergalactic space. But this, too, is a profound illusion. Galaxies are not isolated. They are social creatures drawn together by the relentless pull of gravity into groups, clusters, and superclusters. The Milky Way itself is a prominent member of what we call the local group, a gravitationally bound collection of more than 50 galaxies dominated by our own and our even larger and more massive neighbor, the Great Spiral in Andromeda. And just as individual stars can have close encounters and catastrophic collisions, so too can these cosmic titans. But a galactic collision is a very different kind of event. It is not a sudden, violent crash of two solid objects. The stars themselves are so far apart that direct stellar collisions are almost unheard of. Imagine two swarms of bees flying through each other. The bees themselves would rarely touch. Instead, a galactic collision is a slow, majestic, and utterly transformative process that plays out over hundreds of millions, even billions of years. It is a gravitational dance of destruction and creation on the grandest possible scale, choreographed by the invisible hand of dark matter. These encounters are not rare. They are a fundamental part of galactic evolution. The Hubble Space Telescope and the James Webb Space Telescope have given us a stunning gallery of these interacting galaxies frozen in time at various stages of their destructive ballet. We see galaxies with long, graceful tidal tails of stars being stripped away, galaxies with brilliant bursts of new star formation igniting at their hearts, and galaxies in the final chaotic throes of merging into a single, larger entity. This is an invitation to the galactic dance, a spectacle of unimaginable scale, where the fates of trillions of stars and worlds are decided. To truly understand why galaxies collide, we must first grapple with one of the deepest mysteries in all of science. We must understand what a galaxy truly is. What we see with our telescopes, the beautiful swirling arms of a spiral galaxy, the combined light of its hundreds of billions of stars, its glowing nebulae of gas and dark lanes of dust, is only a tiny fraction of the whole. It is like seeing the bright lights of a sprawling city at night from a great distance without being able to see the city itself, its buildings, its roads, its infrastructure. The visible part of a galaxy is merely the luminous icing on a much larger, darker, and more massive cake. All the normal matter that we can see and interact with the stuff that makes up stars' planets, and us accounts for only about 15% of a galaxy's total mass. So what makes up the other 85%? The answer is one of the most profound and humbling discoveries of modern astronomy: dark matter. This is a mysterious, invisible substance that does not emit, absorb, or reflect any form of light. We cannot see it. We cannot touch it. It passes through us and the entire planet as if we were ghosts. And yet we know it is there. We can detect its presence through its immense gravitational influence on the things we can see. It was an astronomer named Vera Rubin who in the 1970s provided the definitive evidence. She was studying the rotation of spiral galaxies and found something deeply puzzling. The stars on the outer edges of the galaxies were orbiting just as fast as the stars closer to the center. This defied Newtonian physics. If the visible matter were all that existed, these fast-moving outer stars should have been flung off into intergalactic space. The only way they could be held in their orbits was if the galaxy was embedded in a vast, unseen halo of some other kind of matter, a substance whose gravity was holding everything together. This is dark matter. It is the true galaxy. It is the invisible scaffolding, the cosmic backbone upon which the visible structures of the universe are built. When we say that two galaxies are on a collision course, what we really mean is that their enormous overlapping dark matter halos have already begun to interact and merge, their immense gravity pulling them together. The stars themselves are just along for the ride tracers of a much grander and completely invisible gravitational dance. The collisions of giants are choreographed not by the light we see, but by the darkness we cannot. The cosmic dance begins long before the visible galaxies make first contact. As two galaxies approach each other over millions of years, their vast overlapping dark matter halos begin to exert a powerful gravitational drag, like two great invisible hands reaching out across the void. The galaxies, which may have been on a trajectory to simply fly past each other, are slowed and pulled into a mutual decaying orbit. This is the point of no return. Their fate is sealed. The first close pass, the first brush of one galaxy against the other, is a moment of breathtaking, destructive beauty. The immense tidal forces of each galaxy's gravity begin to tear at the other, a gravitational tug-of-war on a scale of 100,000 light-years. Stars themselves are not ripped apart individually. The forces are not strong enough for that. Rather, vast streams of stars and gas are pulled out from the fragile galactic disks like threads being pulled from a spinning tapestry. These streams form long, graceful, and ghostly arcs known as tidal tails. These tails can stretch for hundreds of thousands of light-years into intergalactic space, ethereal bridges of exiled stars connecting the two interacting galaxies. The galaxies themselves become distorted, their elegant pinwheel spiral structures warped and twisted by the gravitational encounter, their ordered rotating disks thrown into chaos. It is cosmic ballet and cosmic demolition rolled into one, a dance of giants choreographed by the unfeeling laws of gravity, playing out in slow motion over eons. But this dance is not always one of equals. The universe is a place of hierarchies. When a large galaxy like our Milky Way encounters a much smaller dwarf galaxy, the result is not a merger, but an act of galactic cannibalism. The larger galaxy's gravity is overwhelming. It systematically strips the dwarf galaxy of its gas and stars, pulling them into its own structure in long, looping stellar streams that orbit the larger galaxy's halo. Over time, the dwarf galaxy is completely disrupted, its stars assimilated, its identity erased. The Milky Way's own vast spherical halo is filled with these stellar streams, the ghostly shimmering remnants of the dozens of dwarf galaxies it has consumed over its long and violent history. We are living in the belly of a beast. This process of hierarchical merging is fundamental to cosmic evolution. Galaxies grow by eating other galaxies. The universe we see today, with its giant elliptical and spiral galaxies, is a product of this relentless, eons-long history of cosmic cannibalism. The cosmic dance is not always one of equals. In this grand gravitational ballet, size matters. When a large galaxy like our Milky Way encounters a much smaller dwarf galaxy, the result is not a merger between partners, but a brutal act of galactic cannibalism. The larger galaxy's gravity is overwhelming. It acts like a cosmic predator, its immense tidal forces stripping the dwarf galaxy of its gas, and stars pulling them away into long, looping stellar streams that orbit the larger galaxy's halo like shimmering ghostly ribbons. Over time, the dwarf galaxy is completely disrupted. Its stars assimilated its identity, erased its heart swallowed whole. The Milky Way's own vast spherical halo is filled with these stellar streams, the faint shimmering remnants of the dozens of dwarf galaxies it has consumed over its long and violent history. We are in fact living inside the belly of a beast. This process of hierarchical merging is fundamental to cosmic evolution. Galaxies grow by eating other galaxies. This is not a theory, it is an observed reality. Astronomers have found numerous examples of this cannibalism in action throughout the universe. We see large galaxies with multiple overlapping stellar streams, the clear evidence of several recent meals. We see the small, dense core of a dwarf galaxy plunging through the disk of a larger spiral, a final act of defiance before it is completely torn apart. The universe we see today, with its giant elliptical and spiral galaxies, is a product of this relentless, eons-long history of cosmic cannibalism. The largest galaxies are not born that way. They are built piece by piece from the wreckage of their smaller neighbors. But when two large gas-rich spiral galaxies of roughly equal size collide, the consequences are even more spectacular. This is not an act of cannibalism, but a battle of titans. While the stars themselves rarely hit each other due to the vast distances between them, the same is not true for the galaxy's enormous diffuse clouds of interstellar gas and dust. As the two galaxies pass through each other, their gas clouds slam together at supersonic speeds, creating massive shock waves that ripple through the merging system. These shock waves compress the gas, triggering a massive and frenetic burst of star formation. An entire galaxy's worth of gas can be converted into new stars in a relatively short period of a few 100 million years. This is a starburst. The merging galaxies light up with the brilliant blue-white light of millions of newborn massive stars. The rate of star formation can be hundreds, even thousands of times greater than in a normal quiescent galaxy like the Milky Way today. The collision, a seemingly destructive event, has ignited a firestorm of creation, transforming the placid galaxies into one of the most fertile and spectacular environments in the entire universe. When two large gas-rich spiral galaxies collide, the consequences are spectacular. While the stars themselves rarely hit each other due to the vast distances between them, the same is not true for the galaxy's enormous diffuse clouds of interstellar gas and dust. As the two galaxies pass through each other, their gas clouds slam together at supersonic speeds, creating massive shock waves that ripple through the merging system. These shock waves compress the gas, triggering a massive and frenetic burst of star formation. An entire galaxy's worth of gas can be converted into new stars in a relatively short period of a few 100 million years. This is a starburst. The merging galaxies light up with the brilliant blue-white light of millions of newborn massive stars. The rate of star formation can be hundreds, even thousands of times greater than in a normal quiescent galaxy like the Milky Way today. The collision, a seemingly destructive event, has ignited a firestorm of creation, transforming the placid galaxies into one of the most fertile and spectacular environments in the entire universe. These starburst galaxies are cosmic nurseries on an industrial scale. The brilliant blue knots of light we see in images of galactic mergers are colossal star clusters, each containing hundreds of thousands to millions of young hot stars, all born together in a single chaotic event. The intense ultraviolet radiation from these massive stars ionizes the surrounding hydrogen gas, causing it to glow with a characteristic and beautiful pinkish-red hue, painting the scene of destruction with the colors of creation. But this frenzy cannot last. The massive, brilliant blue stars that dominate the light of a starburst galaxy burn through their nuclear fuel at a prodigious rate. They live fast and die young, exploding as supernovae after only a few million years. These successive waves of supernova explosions further churn and heat the remaining gas, eventually blowing it out of the galaxy altogether or rendering it too hot and diffuse to form new stars. The starburst is a brief, glorious, and self-limiting event. The collision provides the fuel for a great cosmic fire, but the fire itself consumes the fuel and eventually burns out. The legacy of this creative frenzy is a new, larger galaxy, enriched with the heavy elements from millions of supernovae, but now largely devoid of the cold gas needed to build the next generation of stars. The beautiful spiral arms are gone, replaced by a new, more mature, and much quieter stellar metropolis. To see this process of destruction and creation in action, we need only to look towards the southern constellation of Corvus the Crow. There, some 65 million light-years away from Earth, we find a stunning portrait of a galactic collision in progress. Known to astronomers as NGC 4038 and 4039, they are more famously and poetically called the antennae galaxies. This spectacular pair of interacting galaxies is a textbook example of a major galactic merger, a snapshot of a process that takes hundreds of millions of years to complete, conveniently captured for us at a moment of maximum drama. It is in many ways a glimpse into our own Milky Way's distant future. Images from the Hubble Space Telescope reveal a scene of beautiful luminous chaos. The two galactic cores, the bright, dense hearts of the original spiral galaxies, are still distinct, but their disks are now completely enmeshed in a gravitational tug-of-war. The most striking features are the two long, curving tidal tails that give the system its name. These antennae, flung out into intergalactic space by the powerful tidal forces of the first close encounter stream for hundreds of thousands of light-years, filled with billions of exiled stars, gas, and dust. They are a ghostly testament to the organized spiral structures that have been torn asunder. But where there is destruction, there is also creation. The combined system is ablaze with the light of a furious, ongoing starburst. The regions where the vast clouds of interstellar gas from the two galaxies are colliding are dotted with thousands of brilliant young star clusters. These stellar nurseries glow with the characteristic pinkish-red light of ionized hydrogen gas, a sure sign of massive star formation. The James Webb Space Telescope, with its powerful infrared vision, has peered through the obscuring curtains of dust to reveal even more detail. Its images show the intricate web of gas and dust being funneled down towards the galactic centers, providing the fuel for the starburst and for the two supermassive black holes that lurk within monsters that are about to awaken and feast. The antennae galaxies, are more than just a beautiful picture. They are a cosmic laboratory, allowing us to study the physics of galactic mergers in exquisite detail. They are a portrait of collision, a masterpiece of destruction, and a vibrant canvas of creation. At the heart of nearly every large galaxy, including our own Milky Way, lies a monster. It is a supermassive black hole, an object with the mass of millions or even billions of suns compressed into a volume smaller than our solar system. For most of a galaxy's life, this central monster lies dormant. In a quiet, stable galaxy like the Milky Way today, our central black hole, Sagittarius H is a sleeping giant. It is starved of fuel, accreting only a tiny, insignificant trickle of interstellar gas that happens to wander too close. It is a quiet, brooding presence at the heart of our galactic home. But a galactic merger changes everything. The collision is the universe's ultimate wake-up call. The powerful gravitational forces of the merger act like a giant cosmic egg beater, violently disrupting the stable circular orbits of gas clouds and stars within the two galaxies. This gravitational chaos robs them of their angular momentum, the very thing that was keeping them in safe, distant orbits. As a result, a significant fraction of this interstellar material is funneled inwards, cascading down towards the galactic center in great, dense streams. The sleeping giant awakens. The supermassive black holes at the hearts of the merging galaxies are suddenly presented with an all-you-can-eat buffet of cosmic proportions. This sudden massive influx of gas forms a vast swirling structure around the black hole known as an accretion disk. This disk is a maelstrom of matter heated to millions of degrees by friction and compression as it spirals inwards towards the event horizon. It begins to glow with an incredible, ferocious intensity, a beacon of light powered by the gravitational energy of the black hole's feast. The monster, which had slumbered in darkness for billions of years, has now been awakened by the collision, and in doing so, it will unleash one of the most powerful and luminous phenomena in the entire universe. The galactic collision has not just created new stars, it has fed the central beast, and the consequences will be felt across the entire galaxy. As the supermassive black hole gorges on the torrent of infalling gas, it becomes what astronomers call an active galactic nucleus, or AGN. And the most luminous, most powerful of these are known as quasars. The name is a contraction of quasi-stellar radio source, because when they were first discovered in the 1960s, they appeared as star-like points of light, but were powerful emitters of radio waves, unlike any normal star. The mystery was solved when astronomers realized these were not stars in our own galaxy, but incredibly distant objects, the hyperluminous cores of young active galaxies, billions of light-years away. A quasar is not powered by the black hole itself, but by the gravitational energy of the matter in its accretion disk. As this matter spirals towards the event horizon, it is crushed and heated to millions of degrees, releasing a flood of radiation so intense that it can outshine the combined light of all the hundreds of billions of stars in its host galaxy. For a time, the tiny central engine, no larger than our solar system, becomes the brightest object in its corner of the universe. Quasars are the lighthouses of the cosmos. Because they are so incredibly luminous, we can see them from across the entire observable universe, allowing us to probe the conditions of the distant ancient cosmos. But their influence doesn't stop there. The intense magnetic fields tangled and twisted within the rapidly spinning accretion disk can act like a colossal cosmic particle accelerator. They can seize a fraction of the infalling matter before it reaches the event horizon and launch it outwards in two colossal, tightly focused jets that travel at nearly the speed of light. These relativistic jets are among the largest single structures in the universe. They can plow through the host galaxy and out into intergalactic space, stretching for millions of light-years far larger than the galaxy itself. This process, known as AGN feedback, plays a crucial self-regulating role in the evolution of galaxies. The powerful jets and radiation from the quasar can heat and expel the remaining cold gas from the galaxy, effectively shutting down any further star formation. It is a galactic thermostat. The merger provides the fuel to create a great starburst, but it also awakens the central monster, which then blows away the remaining fuel, ensuring that the galaxy does not grow too large too quickly. The black hole awakened by the chaos of the collision now reshapes the destiny of its entire galaxy in a final dramatic act of cosmic architecture. The cosmic dance cannot last forever. Over hundreds of millions of years, the two galaxies pass through each other multiple times in their decaying orbit. With each pass, their structures become more and more entangled, their individual identities blurring. The violent starburst phase eventually burns itself out, having consumed most of the available cold gas. The brief, brilliant reign of the quasars fades as the central monsters finish their meal and return to a quiet slumber. The chaos subsides. What is left in the aftermath is not a spiral galaxy. The collision has been a great cosmic scrambler, randomizing the once orderly circular orbits of the stars and destroying the fragile rotating disk structure. The result is a new single and much larger galaxy. This new entity is typically a giant elliptical galaxy, a vast reddish and somewhat featureless swarm of stars. It is shaped like a flattened sphere or a colossal football, with its stars moving on random disorganized beehive-like orbits. Having used up or blown away most of its gas in the starburst and quasar phases, it has very little raw material left for new star formation. Its stellar population is dominated by older, cooler, redder stars. It is, in a sense, a red and dead galaxy, a mature and quiescent stellar metropolis that has settled into a long and quiet old age after a violent and spectacular youth. But this is not an end. It is a transformation. The two spiral galaxies, with their vibrant star-forming regions and elegant structures, have been destroyed. But from their wreckage, a new, more massive and more stable cosmic entity has been born. The process of cosmic evolution has taken another step forward. The merger has gathered an enormous amount of mass into one place, creating a dominant galaxy that will now anchor its local corner of the universe. And eventually the two supermassive black holes from the cores of the original galaxies, having sunk to the center of the new elliptical, will themselves find each other. They will enter their own final silent death dance, spiraling together and merging in a final powerful burst of gravitational waves that will ring out across the cosmos, the last dying echo of the great collision. A new beginning has been forged from the ashes of the old. This story of galactic collision of destruction and ultimate creation is not just an abstract tale of distant objects in the far-flung cosmos. It is the story of our own future. Our nearest large galactic neighbor, the great spiral galaxy in Andromeda, is currently about 2.5 million light-years away from us. From a dark sky site, it is visible to the naked eye as a faint, fuzzy patch of light, the most distant object the average person can see without a telescope. It is our cosmic twin, slightly larger and more massive than our own Milky Way, containing perhaps 1 trillion stars to our few hundred billion. And it is not staying where it is. It is hurtling towards us. For centuries, astronomers did not know if Andromeda was moving towards us, away from us, or simply moving sideways relative to our position. Its sheer distance made its motion incredibly difficult to measure. But by using the Hubble Space Telescope to painstakingly track the subtle sideways motion of stars within Andromeda against the background of even more distant galaxies, and by precisely measuring the Doppler shift of its starlight, we now know the truth. Andromeda is heading almost directly for us at a blistering speed of about 110 kilometers per second. That's fast enough to travel from New York to Los Angeles in under a minute. There is no doubt, we are on a collision course. This is not a possibility. It is a destiny, written in the unyielding laws of gravity. Our two galaxies, the dominant members of our local group, are the two most massive objects in our corner of the universe. They are inevitably falling towards each other, pulled together by the gravity of their enormous, overlapping dark matter halos. In about 4.5 billion years, our two majestic spiral galaxies will begin their first close pass. The great dance of destruction and creation, the same dance we have witnessed in the antenna galaxies, will begin in our own cosmic backyard. The night sky of a future Earth, should it still exist, will be a spectacle beyond our wildest dreams, as the great sprawling spiral of Andromeda grows to fill the heavens, a beautiful and terrifying harbinger of our galaxy's final transformative act. This is our cosmic destiny, a fate that was sealed billions of years ago. How can we possibly predict an event that is billions of years in the future? With any confidence, we cannot run the experiment, but we can do the next best thing. The answer lies in the immense power of supercomputer simulations. By inputting our best measurements of the current positions, velocities, and masses, including the all-important dark matter of the Milky Way, Andromeda, and the other smaller galaxies in our local group, astronomers can create a virtual cosmic laboratory. They can then apply the known laws of physics and gravity and run the clock forward, watching the future of our galactic neighborhood unfold in a matter of hours or days. These powerful N-body simulations, which track the gravitational interactions of billions of virtual stars and dark matter particles, all paint a remarkably consistent picture of our future. They show a long, protracted, and spectacular merger process. The first close pass, the first brush between the two galaxies' outer disks, will happen in about 4.5 billion years. This first encounter will dramatically distort both galaxies, pulling out vast luminous tidal tails of stars and gas. The two galaxies will then separate their momentum, carrying them apart, only to be inevitably pulled back together by their mutual gravity for a second, even more disruptive pass a billion or so years later. After several such passes, their orbital energy will have been dissipated, and their cores will finally merge in about 6 to 7 billion years from now. The prophecy of the simulations is clear. The result of this great merger will be a new single giant elliptical galaxy, a vast reddish and largely featureless swarm of stars. Some astronomers have already given this future galactic behemoth a nickname, Milkomeda. Our familiar beautiful spiral home, the galaxy that has nurtured our star and our planet for its entire existence, will be gone. Its elegant structure erased its identity, merged into something new and grander. It will be replaced by a vast reddish swarm of stars on chaotic orbits, the quiet and mature product of a violent and spectacular youth. This is the Milkomeda prophecy, a glimpse into a future written not in the stars, but for the stars. What will this cosmic collision mean for our Sun, our Earth, and our solar system? The computer simulations offer a surprising and somewhat reassuring answer. While the galaxy as a whole will be completely restructured in a chaotic and violent process, the chances of our Sun directly colliding with another star from Andromeda are infinitesimally small. The space between the stars, even during a galactic merger, is simply too vast. Our solar system will almost certainly survive the merger intact. But that does not mean we will escape unscathed. Our cosmic address is about to change dramatically and permanently. The simulations show that it is highly likely, a probability of perhaps 90%, that during one of the close passes between the two galaxies, our solar system will be gravitationally ejected from its current quiet position in what was the Milky Way's disk. We will be flung out into a new, long, looping and chaotic orbit within the newly forming Milkomeda galaxy. Where will we end up? It's impossible to know for sure. We could be sent far out into the galactic halo, the vast, sparse sphere of old stars that surrounds the main body of the galaxy. From this distant vantage point, we would have a spectacular panoramic view of the entire merger unfolding over hundreds of millions of years. Or we could be plunged deep towards the chaotic galactic center, where the two supermassive black holes, each with the mass of millions of suns, are in the final violent process of merging. There is a small, but not zero, chance that we could be ejected from the new galaxy, entirely cast out into the lonely darkness of intergalactic space, to become a rogue solar system, a fate similar to that of the exiled planets we have already discussed. But the most likely outcome is that we will find a new home, a new orbit within the great reddish swarm of stars that is Milkomeda. Our familiar beautiful view of the Milky Way's band of light across the night sky, a sight that has inspired awe and wonder in humanity for our entire existence, will be gone forever. It will be replaced by a very different and, for a time, a much more spectacular and terrifying celestial vista. Our home will survive, but it will be a home in a very different kind of galaxy. Let us imagine for a moment the view from a future Earth, assuming our planet survives the Sun's own inevitable evolution into a red giant. In the millions of years leading up to the first close pass, the Andromeda Galaxy will grow ever larger and more magnificent in our night sky. It will transform from a faint, fuzzy smudge into a breathtaking, sprawling spiral that dominates the heavens, a celestial spectacle unmatched in human history. Then, as the collision begins in earnest, the sky will ignite. We will see the bright blue knots of new star-forming regions, colossal stellar nurseries, igniting where the gas clouds of the two galaxies collide and compress. We will see the great, ghostly tidal tails of stars, our sun's former neighbors, stretching across the heavens in luminous arcs. The sky will no longer be a dark, static canvas with pinpoints of light, but a swirling, dynamic, and violent masterpiece of cosmic creation. As our solar system is flung into its new chaotic orbit, our perspective on this cosmic drama will constantly change. One millennium, we might pass through a dense, newly formed star field, the night sky ablaze with the light of a billion unfamiliar suns. The next, we might be flung far out into the galactic halo, with a lonely but spectacular view, looking back at the magnificent disordered spectacle of the newly forming Milkomeda. Any future inhabitants of Earth will be witness to the greatest and longest fireworks show in our planet's history, a final beautiful and terrifying testament to the galaxy that was once our home. There is a strange and beautiful irony in this cosmic forecast. The collision that will destroy our Milky Way galaxy is set to begin in roughly 4.5 billion years. But our own sun is also a ticking clock. In about 5 billion years, it will exhaust the hydrogen fuel in its core and begin to swell into a red giant, its outer layers expanding to engulf the orbits of Mercury, Venus, and almost certainly the Earth. Our planet is destined to be sterilized and then consumed by our own star at almost the same cosmic moment that our galaxy is being torn apart. It is a strangely poetic and synchronized end, a reminder that on every scale, from the stellar to the galactic, the universe is in a constant state of violent and beautiful transformation. Our sky and our world will end in fire. The hierarchy of cosmic collisions does not end with galaxies. Our journey now takes its final and most dramatic leap in scale to the largest gravitationally bound structures in the entire universe, galaxy clusters. If galaxies are cities, then clusters are sprawling, continent-sized metropolitan areas. They can contain hundreds or even thousands of individual galaxies, all bound together by their mutual gravity and embedded in an enormous diffuse cloud of superheated gas and an even larger halo of dark matter. These clusters are the true titans of the cosmos, the great crossroads of the universe. And even these colossal structures can collide. This is the ultimate cosmic demolition. When two galaxy clusters, each with a total mass of over a quadrillion suns, merge, it is the most energetic event in the universe since the Big Bang itself. The individual galaxies within the clusters, much like the individual stars in a galactic merger, largely pass through each other, like ghosts, their vast internal distances, ensuring very few direct collisions. But the enormous clouds of intergalactic gas that fill the space between the galaxies are not so lucky. These gas clouds, which contain far more normal matter than all the stars in the cluster combined, slam into each other at speeds of thousands of kilometers per second. This creates a colossal shockwave that heats the gas to unfathomable temperatures, tens of millions of degrees, causing it to glow brilliantly in X-ray light, which can be seen by our space-based X-ray observatories, like the Chandra X-ray Observatory. The most famous and scientifically important example of this is a system known as the Bullet Cluster. Here we see two galaxy clusters that have recently passed through each other at high speed. In the X-ray image, we can see the hot gas from each cluster shaped like a bullet, and its bow shock, which has collided and slowed down near the center of the merger. But when we map the total mass of the system, using a technique called gravitational lensing, we find something astonishing. The vast majority of the mass, the dark matter, has passed straight through the collision unimpeded, as if the gas were not even there. We can see the galaxies and the dark matter on one side of the collision, and the hot gas, the normal matter, lagging behind on the other. This spatial separation of the gas from the overall mass is considered the most direct and powerful observational proof we have for the existence of dark matter. The collision of giants has, in a single spectacular event, revealed the universe's invisible backbone. On the very largest scales of hundreds of millions of light years, the universe is not a random uniform assortment of matter. Supercomputer simulations of the evolution of the cosmos, combined with deep surveys of the positions of millions of galaxies, have revealed a breathtaking and beautiful underlying structure. It is known as the cosmic web. This web is the universe's grandest architectural project, a vast, intricate, and interconnected network that fills the entire cosmos. It consists of long, tenuous filaments of dark matter and primordial gas stretching like a cosmic spider's web across billions of light years. Where these filaments intersect, they form dense, massive knots, and it is within these gravitational crossroads that the great galaxy clusters are found. The vast, empty, and strangely beautiful regions between the filaments are called cosmic voids. This cosmic web is not a static structure. It is the dynamic framework along which the universe evolves. Matter, both dark and normal, flows along the filaments drawn by the relentless pull of gravity from the voids towards the dense nodes. Galaxies form and are lit up along these filaments and are then funneled down these cosmic superhighways into the bustling metropolitan areas of the clusters, where they interact, merge, and evolve. The collision and merger of galaxy clusters themselves are the primary way that these nodes in the cosmic web grow, becoming ever more massive and dominant over cosmic time. The universe's architecture is a product of this relentless top-down process of gravitational collapse and collision. The violent encounters we have witnessed throughout our journey from the smallest asteroid impact to the grand merger of galaxy clusters are not isolated random events. They are the fundamental mechanism by which the universe organizes itself. They are the process of cosmic construction. Gravity provides the blueprint, the dark matter provides the invisible scaffolding, and the collisions, mergers, and cataclysms are the builders, the cosmic laborers, who are slowly and patiently weaving the beautiful and complex tapestry of the cosmic web over the course of 13 billion years. The universe is not just a collection of things. It is a process, a single unfolding story of structure being built from chaos. Our journey is almost at an end. We have traveled from the violent birth of our own moon to the majestic and intricate weaving of the cosmic web. We have seen how a single random asteroid impact can rewrite the entire history of life on a planet. We have witnessed the dramatic death dance of stellar corpses forging the universe's precious metals in a brilliant flash of gravitational waves and light. And we have watched as entire galaxies, great cosmic cities of stars, are torn apart, cannibalized, and reassembled into new, grander structures. At every single scale, from the planetary to the stellar to the galactic and beyond, the story is the same. The universe is not a quiet, static, and peaceful place. It is a dynamic, evolving, and often breathtakingly violent system, and its primary agent of change, its most fundamental tool of creation, is the collision. What might appear to our human sensibilities as senseless destruction is in fact part of a grand and intricate design. It is a symphony of violence that is constantly reshaping the cosmos, driving it towards ever greater levels of complexity and structure. From the smallest moon to the largest supercluster, everything we see is the product of a long and chaotic history of cosmic encounters. The serene, beautiful universe we see in the night sky is an illusion, a momentary snapshot of a single quiet frame in a long and epic film of cosmic violence. We are living in the beautiful, complex wreckage of 13 billion years of collisions. The great cosmic forge is never idle, and the symphony is far from over. Let us now redefine our understanding of these cosmic events. A collision is not an accident. It is not a flaw in the grand cosmic design. It is the design. A cosmic collision is not just an act of destruction. It is the fundamental engine of cosmic evolution. It is the ultimate recycling program operating on a scale of planets, stars, and galaxies. Think of the journey of matter through the cosmos. The collision of protoplanets in the chaotic early solar system assembled the worlds we know today from smaller scattered fragments. The explosive merger of two white dwarfs, a collision of stellar ghosts, creates the brilliant standard candles that allow us to measure the universe's expansion and probe its deepest mysteries. The even more violent collision of two neutron stars, a crash of stellar zombies, forges the universe's heaviest elements and seeds the interstellar medium with the raw materials for future worlds and perhaps for life. And the majestic slow-motion collision of two galaxies builds larger, more massive structures and triggers the brilliant bursts of star formation that create the next generation of suns. At every single stage, matter and energy are not lost in these events. They are simply reconfigured, transformed, and recycled into new and often more complex forms. Destruction, it seems, is not an end in the cosmic lexicon. It is a vital, necessary, and ultimately creative step in the universe's unending process of self-creation and evolution. The cosmos is not a static museum of finished works. It is a dynamic and constantly churning workshop. And the collision in all its terrifying and beautiful forms is its primary and most powerful tool. It is the hammer and the anvil of the cosmic forge, constantly breaking down the old to build the new. We are living proof of this process. The very fact that a complex planet like Earth and complex beings like us can exist is a testament to the creative power of this cosmic recycling program, and so we arrive at the most profound and personal truth of all. The violence of the cosmos, the unending symphony of cataclysmic collisions, is the very reason we are here to ponder it. We are not just distant, detached observers of this cosmic drama. We are its direct descendants, its children. We are born from the ashes of ancient stellar explosions and shaped by the gravitational chaos of cosmic encounters. The gift of cataclysm is the gift of existence itself. Think of the chain of events. The cataclysmic impact that formed our moon gave us the stable climate and the rich tidal environments that may have been crucial for the emergence of life. The supernova explosions of countless long-dead stars scattered across our galaxy over billions of years created the very atoms that make up our bodies and our world. The carbon in our DNA, the oxygen we breathe, the iron in our blood, we are literally made of stardust, the recycled remnants of stellar furnaces. The even more violent collision of neutron stars forged the heavy elements that made our technological civilization possible. The chaotic process of galactic mergers and starbursts playing out over cosmic eons created the stable, enriched galactic environment in which a star like our Sun and a planet like our Earth could form in the first place. And the impact that wiped out the dinosaurs, a terrible cataclysm for them, was a moment of profound opportunity for our distant mammalian ancestors. It cleared the stage, opening up the ecological niches that would allow mammals to diversify and eventually evolve into the intelligent, self-aware beings who can build telescopes and look back out at the universe to piece together this extraordinary story of our own violent origins. You are not just an observer of this cosmic drama. You are one of its greatest and most unlikely achievements. You are a piece of the universe that has, for a brief and precious moment, evolved the capacity to know itself. We are the legacy of 1 billion ancient collisions, the living embodiment of the universe's creative power, the gift of cataclysm made manifest. Let us then, in the final moments of our journey, redefine the word collision. In our everyday language, it is a word synonymous with accident, with failure, with a violent and unwelcome end. But in the language of the cosmos, its meaning is transformed. It is not merely an impact. It is a transfer of energy and a reshaping of orbits. It is the catalyst for the formation of moons and planets. It is the trigger for the nucleosynthesis of the universe's heaviest elements. It is the mechanism of galactic growth and the spark that ignites a firestorm of new star formation. It is the source of the gravitational waves that allow us to listen to the dark, hidden side of the universe. In the grand cosmic dictionary, collision is a synonym for change, for interaction, for evolution. Without it, the universe would be a far more simple, static, and ultimately sterile place. The primordial hydrogen and helium forged in the heat of the Big Bang would have remained just that diffuse uniform and unchanging. There would be no stars to light up the darkness, no heavy elements to provide the building blocks of complexity, no rocky planets to provide a stable home, and certainly no life to ponder its own existence. The universe isn't just a random collection of matter and energy scattered by a primordial explosion. It is a masterpiece of precision and structure, and its primary tool of creation, its most fundamental process, is the very violence that we, from our fragile human perspective, find so terrifying. The beautiful, complex, and life-giving universe we inhabit is not an accident that happened in spite of the violence. It is a direct and necessary consequence of it. The collisions are not a bug in the system. They are the most important feature. Our journey through the universe's most extreme collisions has shown us that this fundamental process is ongoing, a core aspect of the cosmos, from its fiery past to its distant, unknowable future. The great cosmic dance continues, and it is far from over. Planets will continue to be ejected from their stellar systems, becoming lonely wanderers in the galactic night. Neutron stars locked in their gravitational death spirals will continue to merge, forging the universe's heavy elements and singing their gravitational wave songs. And galaxies will continue their slow, majestic ballet of destruction and creation. Our own Milky Way and Andromeda will perform this dance, and the great Milkometa galaxy that results will, in the far, far future, likely continue the process, merging with other galaxies in our Virgo supercluster. The story of cosmic collisions is far from over because our ability to witness them has just begun. With the advent of gravitational wave astronomy, we have opened a new window onto the dark universe, and we are only just beginning to listen to the symphony of its most violent events. What other more exotic collisions await discovery in the ripples of space-time? What happens when a star collides directly with a supermassive black hole? What secrets will we uncover as our gravitational wave detectors become ever more sensitive, allowing us to hear the faint whispers from the very dawn of time? The cosmic forge is never idle. The unending dance of gravity and matter will continue to shape and reshape the universe for billions, even trillions of years to come. As we continue to gaze out into the cosmic darkness, we do so with a newfound and profound understanding. We know that we are not looking at a peaceful, static void, but at an active, vibrant, and violent arena of creation. And we are left with a final, humbling, and unanswered question as the universe continues its unending dance of transformation. What new wonders, what new terrors, and what new forms of complexity will it create next? The story is still being written, and we have been given the brief, precious privilege of reading a single spectacular page. The next time you gaze up at the silent stars, remember that you are witnessing the quiet aftermath of a billion ancient battles. Our universe is not a tranquil kingdom. It is a violent and beautiful forge, and we, in all our fragility, are its most unlikely creation. As this unending dance of destruction and creation continues, what new wonders will be born from the next great cosmic collision? What are your thoughts on our violent creative cosmos? Let us know in the comments below. Thank you for watching Astro Horizons. If you enjoyed this journey into the fire, don't forget to subscribe to Astro Horizons and hit the notification bell for more voyages into the heart of the cosmos.